The National Electrical Code, or NEC, does not specifically require grounding the secondary of a delta-delta transformer. However, there are circumstances where grounding may be necessary or recommended. For transformers with secondary currents exceeding 50 amps, the NEC recommends grounding one corner of the secondary. This limits the voltage to ground in case of a fault to 120 volts or less. Grounding the secondary can also provide a path for fault currents to flow, protecting equipment and personnel from electrical shocks. National Electrical Manufacturers Association, or NEMA, standards generally recommend grounding the secondary of delta-delta transformers. The NEC does not have a specific requirement for installing a ground detection system for delta-delta transformers. However, it may be a prudent practice to consider installing one. A ground detection system can provide an early warning of a developing ground fault, allowing for prompt corrective action before it becomes a major issue. Furthermore, a ground detection system can help ensure that personnel are not exposed to dangerous conditions caused by unintended grounding. While the NEC does not explicitly require grounding the secondary of a delta-delta transformer, it is often recommended for safety and reliability reasons. Installing a ground detection system is also a prudent practice to provide early warning of potential ground faults. Ultimately, the decision on whether or not to ground or install a ground detection system should be based on a risk assessment and the specific conditions of the installation. Let's delve into grounding recommendations in more detail. Grounding the secondary of a delta-delta transformer offers several benefits, particularly when dealing with high currents. When secondary currents exceed 50 amps, grounding one corner of the secondary is recommended by the NEC. This practice serves to limit the voltage to ground in the event of a fault. Specifically, it aims to keep the voltage at or below 120 volts. The purpose here is to mitigate the risk of electrical shock and equipment damage during fault conditions. Electrical safety is a paramount concern in any electrical system. Grounding the secondary of a delta-delta transformer plays a crucial role in enhancing safety. It provides a designated path for fault currents to flow. This path allows overcurrent protection devices, such as circuit breakers or fuses, to quickly detect and interrupt the fault. By promptly clearing the fault, grounding helps protect both equipment and personnel from electrical shocks and other hazards. NEMA standards offer valuable guidance on best practices for electrical equipment. NEMA generally recommends grounding the secondary of delta-delta transformers. Following NEMA standards helps ensure that installations adhere to industry-accepted safety and performance criteria. Now let's explore ground detection systems and their benefits. Although the NEC does not mandate the installation of ground detection systems for delta-delta transformers, they can be a worthwhile addition to any electrical system. A ground detection system provides an early warning of developing ground faults. This early warning enables proactive intervention and corrective action before the fault escalates into a major issue. By addressing potential problems early, ground detection systems minimize downtime and prevent costly repairs. Moreover, ground detection systems contribute significantly to improved safety. They help ensure that personnel are not exposed to dangerous conditions resulting from unintended grounding. By promptly identifying and addressing ground faults, these systems mitigate the risk of electrical shock and other hazards, creating a safer working environment. Now let's look more deeply into other grounding considerations. While the NEC does not explicitly mandate grounding the secondary of a delta-delta transformer, there are compelling reasons to consider it. Grounding offers enhanced safety and improved reliability of the electrical system. By providing a low impedance path for fault currents, grounding helps protect equipment and personnel from electrical hazards. Furthermore, grounding can improve the stability and performance of the electrical system by minimizing voltage fluctuations and reducing the risk of transient overvoltages. Conversely, ungrounded systems can offer benefits in certain applications. Ungrounded systems can continue to operate during a single ground fault, allowing for uninterrupted operation in critical processes. However, ungrounded systems can also be more difficult to troubleshoot and may pose a greater risk of overvoltages during subsequent faults. Ultimately, the decision to ground or not to ground the secondary of a delta-delta transformer depends on a variety of factors, including the specific application, the risk tolerance of the facility, and the recommendations of a qualified electrical engineer. Ground detection systems play a crucial role in maintaining the safety and reliability of electrical systems, particularly in grounded or impedance-grounded systems. These systems continuously monitor the electrical system for the presence of ground faults and provide an alarm or indication when a fault is detected. Ground detection systems typically consist of a ground fault sensor, a monitoring relay, and an alarm or annunciation device. The ground fault sensor detects the presence of ground fault current, which is the current that flows through the grounding conductor or the earth when a fault occurs. The monitoring relay interprets the signal from the ground fault sensor and activates an alarm or annunciation device when a fault is detected. Ground detection systems offer several benefits, including early warning of ground faults, improved safety, and reduced downtime. By detecting ground faults early, these systems allow for prompt corrective action before the fault escalates into a major problem. This can help prevent equipment damage, reduce the risk of electrical shock, and minimize downtime. There are several types of ground detection systems available, each with its own advantages and disadvantages. Some common types include resistive ground detection, capacitive ground detection, and differential ground detection. Resistive ground detection uses a resistor to limit the ground fault current and provide a voltage signal that is proportional to the fault current. Capacitive ground detection uses a capacitor to block the flow of direct current while allowing alternating current to flow through the grounding conductor. Differential ground detection compares the current flowing into a circuit with the current flowing out of the circuit. If there is a difference between the two currents, it indicates the presence of a ground fault. The selection of the appropriate ground detection system depends on several factors, including the type of electrical system, the size of the load, and the desired level of sensitivity. A qualified electrical engineer can help determine the best ground detection system for a particular application. Risk assessment is a crucial step in determining whether to ground the secondary of a delta-delta transformer or install a ground detection system. A risk assessment involves identifying potential hazards, evaluating the likelihood and severity of those hazards, and implementing appropriate control measures to mitigate the risks. Some factors to consider when conducting a risk assessment include the type of equipment being powered by the transformer, the presence of sensitive electronic equipment, the potential for human contact with energized parts, and the consequences of a ground fault. If the risk assessment reveals a significant risk of electrical shock or equipment damage due to a ground fault, then grounding the secondary of the transformer or installing a ground detection system may be warranted. The specific conditions of the installation should also be taken into account when making a decision about grounding or ground detection. For example, if the transformer is located in a wet or damp environment, the risk of a ground fault may be higher, and grounding the secondary may be more important. Similarly, if the transformer is supplying power to critical equipment, a ground detection system may be necessary to ensure that faults are detected and corrected quickly. In conclusion, while the NEC does not explicitly require grounding the secondary of a delta-delta transformer, it is often recommended for safety and reliability reasons. Installing a ground detection system is also a prudent practice to provide early warning of potential ground faults. Ultimately, the decision on whether or not to ground or install a ground detection system should be based on a risk assessment and the specific conditions of the installation. Consulting with a qualified electrical engineer is recommended to ensure that the electrical system is designed and installed in accordance with applicable codes and standards. Now let's delve into specific sections of the NEC that relate to grounding and bonding. Although there isn't a single section dedicated solely to delta-delta transformer grounding, several articles within the NEC address grounding and bonding requirements for electrical systems in general, and these principles apply to transformer installations as well. NEC Article 250 Grounding and Bonding is the cornerstone of electrical safety. It outlines the general requirements for grounding and bonding electrical systems to ensure a low impedance path for fault current and to minimize the risk of electrical shock. This article covers various aspects of grounding, including system grounding, equipment grounding, and bonding of metal parts. NEC Article 450 Transformers specifically addresses requirements for transformer installations. While it doesn't mandate grounding for delta-delta secondaries, it does provide guidelines for transformer overcurrent protection, disconnecting means, and other safety considerations. This article also references other NEC sections that may be relevant to transformer grounding, such as Article 250. NEC Article 310, Conductors for General Wiring, provides requirements for conductor sizing and insulation. It includes tables and calculations for determining the appropriate size of grounding conductors based on the size of the overcurrent protection device. Proper conductor sizing is crucial for ensuring that the grounding system can effectively carry fault current and protect equipment and personnel. NEC Article 384, Switchboards and Panel Boards, covers the installation and wiring of switchboards and panel boards, which are often used to distribute power from transformers to various loads. This article includes requirements for grounding and bonding of switchboards and panel boards to ensure a safe and reliable electrical system. NEC Table 250.122 provides minimum sizes for equipment grounding conductors for grounding raceway and equipment. Remember, the NEC is a comprehensive document, and it's crucial to consult the latest edition and any applicable local amendments to ensure compliance. Additionally, it's always recommended to seek guidance from a qualified electrical inspector or engineer to ensure that electrical installations meet all applicable requirements. Now we can talk about the different types of ground fault protection. Ground fault protection is a critical safety measure in electrical systems designed to quickly detect and interrupt ground faults, minimizing the risk of electrical shock and equipment damage. There are several types of ground fault protection available, each with its own strengths and weaknesses, and the selection of the appropriate type depends on the specific application and the characteristics of the electrical system. Ground fault circuit interrupters, or GFCIs, are widely used in residential, commercial, and industrial settings to protect personnel from electrical shock. GFCIs continuously monitor the current flowing in the hot and neutral conductors of a circuit, and if they detect a difference of 5 mA or more, they quickly trip the circuit, interrupting the flow of electricity. GFCIs are typically installed in outlets, circuit breakers, or portable devices. Ground fault equipment protection, or GFEP, is designed to protect equipment from damage caused by ground faults. GFEP systems typically use a ground fault sensor to detect ground fault current and a relay to trip a circuit breaker or other disconnecting means. GFEP systems are commonly used in industrial facilities, data centers, and other applications where equipment downtime can be costly. Ground fault protection for equipment, or GFPE, is similar to GFEP, but it is specifically designed to protect electrical equipment from damage caused by arcing ground faults. Arcing ground faults can generate intense heat and cause significant damage to equipment, and GFP systems are designed to quickly detect and interrupt these faults, minimizing the risk of equipment failure and fire. Solidly grounded systems are electrical systems where the neutral point of the transformer or generator is directly connected to ground. Solidly grounded systems provide a low impedance path for ground fault current, allowing for quick detection and interruption of faults. However, solidly grounded systems can also experience high fault currents, which can damage equipment and disrupt operations. Impedance grounded systems use a resistor or reactor to limit the ground fault current. Impedance grounded systems offer a compromise between solidly grounded and ungrounded systems, providing some of the benefits of both. They limit the ground fault current to a safe level, while still allowing for detection and interruption of faults. Ungrounded systems are electrical systems where the neutral point of the transformer or generator is not connected to ground. Ungrounded systems can continue to operate during a single ground fault, allowing for uninterrupted operation in critical processes. However, ungrounded systems can also be more difficult to troubleshoot and may pose a greater risk of overvoltages during subsequent faults. The NEC provides detailed requirements for ground fault protection in Article 230.95, which covers ground fault protection for services, and in Article 517.17, which covers ground fault protection for healthcare facilities. These articles specify the types of ground fault protection that are required in different applications, as well as the testing and maintenance requirements for these systems. Another aspect to consider is voltage imbalance. Voltage imbalance, also known as voltage unbalance, refers to a condition in a three-phase power system where the voltages in the three phases are not equal in magnitude or are not 120 degrees apart in phase angle. Voltage imbalance can have detrimental effects on electrical equipment, including motors, transformers, and electronic devices. It can cause increased motor heating, reduced motor efficiency, increased transformer losses, and malfunctioning of sensitive electronic equipment. There are several causes of voltage imbalance, including unbalanced loads, faulty transformers, and open or high impedance connections. Unbalanced loads are the most common cause of voltage imbalance. When the loads in the three phases of a power system are not equal, it creates a voltage imbalance. Faulty transformers can also cause voltage imbalance. A transformer with a shorted winding or an open circuit can create a voltage imbalance in the power system. Open or high impedance connections can also cause voltage imbalance. A loose connection or corroded contact can create a voltage drop in one or more phases, leading to a voltage imbalance. There are several ways to mitigate voltage imbalance, including balancing loads, replacing faulty transformers, and repairing or replacing open or high impedance connections. Balancing loads involves distributing the loads evenly across the three phases of the power system. This can be achieved by carefully planning the placement of equipment and by using load balancing devices. Replacing faulty transformers is necessary to eliminate voltage imbalance caused by transformer problems. Regular maintenance and testing of transformers can help identify and correct potential problems before they lead to voltage imbalance. Repairing or replacing open or high impedance connections is essential to ensure that all connections are tight and corrosion-free. Regular inspections of electrical connections can help identify and correct potential problems before they lead to voltage imbalance. The National Electrical Manufacturers Association, or NEMA, has developed standards for voltage imbalance. NEMA Standard and G1 provides guidelines for dirting motors operating under voltage imbalance conditions. This standard specifies the amount of dirting required based on the percentage of voltage imbalance. Monitoring voltage imbalance is essential for maintaining the health and reliability of electrical equipment. Voltage imbalance can be monitored using a variety of devices, including voltage meters, power quality analyzers, and data loggers. Regular monitoring of voltage imbalance can help identify and correct potential problems before they lead to equipment damage or failure. Harmonic distortion is another important consideration in electrical systems. Harmonic distortion refers to the presence of harmonic currents and voltages in an electrical system. Harmonics are multiples of the fundamental frequency of the power system, which is typically 60 Hz in the United States. Harmonic distortion can be caused by a variety of nonlinear loads, such as variable frequency drives, electronic ballasts, and computers. Harmonic distortion can have several detrimental effects on electrical equipment, including increased equipment heating, reduced equipment life, and malfunctioning of sensitive electronic equipment. Harmonic distortion can also interfere with communication systems and cause nuisance tripping of circuit breakers. There are several ways to mitigate harmonic distortion, including using harmonic filters, installing line reactors, and using power factor correction capacitors. Harmonic filters are designed to block or reduce the flow of harmonic currents. Line reactors are used to reduce the harmonic currents generated by variable frequency drives. Power factor correction capacitors can help reduce the harmonic distortion caused by nonlinear loads. The Institute of Electrical and Electronics Engineers, or IEE, has developed standards for harmonic distortion. IEE Standard 519 provides guidelines for harmonic voltage and current limits in electrical power systems. This standard specifies the maximum allowable harmonic distortion levels at different points in the power system. Monitoring harmonic distortion is essential for maintaining the health and reliability of electrical equipment. Harmonic distortion can be monitored using a variety of devices, including harmonic analyzers, power quality analyzers, and data loggers. Regular monitoring of harmonic distortion can help identify and correct potential problems before they lead to equipment damage or failure. Power quality is a broad term that encompasses various aspects of the electrical power supply, including voltage stability, frequency stability, harmonic distortion, and transient disturbances. Poor power quality could have a significant impact on the performance and reliability of electrical equipment. Voltage sags and swells can cause equipment to malfunction or shut down. Frequency variations can affect the operation of sensitive electronic equipment. Harmonic distortion can cause equipment heating and reduce equipment life. Transient disturbances, such as lightning strikes and switching surges, can damage or destroy electrical equipment. There are several steps that can be taken to improve power quality, including installing power conditioning equipment, using surge suppressors, and implementing proper grounding and bonding practices. Power conditioning equipment, such as voltage regulators and non-interruptible power supplies, can help maintain a stable voltage supply. Surge suppressors can protect equipment from transient disturbances. Proper grounding and bonding practices are essential for minimizing the risk of electrical shock and equipment damage. Regular monitoring of power quality can help identify and correct potential problems before they lead to equipment damage or failure. Power quality can be monitored using a variety of devices, including power quality analyzers, data loggers, and event recorders. The information provided here is for general guidance only and should not be considered a substitute for professional engineering advice. Always consult with a qualified electrical engineer or other qualified professional before making any decisions about electrical installations.